you should be able to see them. Right. Yeah, right. Juiced up the emphasis pretty high. Try the different domains. Basically, we're at the point now where it's just yeah, I mean, you can figure that to work. Just build a nice stream of population on it. Like, I'm pretty sure that's a line where you're away from being they had to do something. I didn't think about it. I started doing like evaluation with processing too. It's like the F1 application matrix. So just a few days ago, they released 0.5. Yeah, I drove it. Which is not I'm not sure. But when I saw it, I was like, oh, huh. We did so the approximation stuff looks like it works really well.
Don't too close.
Yeah. So I think the way
all the buses were overloaded today. I had to walk.
Sorry?
All the buses were overloaded. I had to walk. I didn't want to take all the snow today, so I just took the bus. But that was a bad choice.
So you have to walk all the way here?
Yes, 50 minutes. Still.
Good early morning bus walk.
I'm sweating now.
yeah.
Okay, let's get started. So welcome to 677. I'm going to be the instructor. My name is Prashant. And so today we'll deal with some of the course logistics, registration, and syllabus, as well as do a quick introduction. Okay. Okay, so the syllabus, if you are already registered for the class, you should have received an email from me yesterday with the course URL. There is a syllabus on there. I'm going to review that briefly. Okay. Just some quick logistics that the course URL is here. I will put a link from my home page. So that is the place where we are going to be posting all the course notes, lab assignments, homework assignments, and so on. Okay. So you need to make sure you keep up with whatever announcements are there. The TA for the course is going to be Manjunath Narayan. He is a graduate student here. And I will post his office hours shortly. I haven't actually had a chance to get him to tell me what they are going to be. So as soon as we know what they are, I'm going to post them. I'm going to have him come to the next class so we can introduce him to all of you, so you know who the TA for the course is going to be. Okay. My office hours are going to be right after class on Monday, or if you have conflict, then you can email me. We'll get an appointment. All right. Now, as far as the course is concerned, there is a sign-up sheet going around. Okay. The classroom section is completely full. Okay. If you haven't registered for the class yet, there is just no way for me to accommodate. We shouldn't really have students standing here because there are exactly as many seats as people who are registered. Okay. Are there people who came today who are not registered? There's a whole bunch of you who are not registered. Okay. So what I would suggest is you write your name on the sign-up sheet. There is a classroom section. There are 35 students registered. There are 35 seats. There isn't much I can do. I tried to get a larger room. There isn't one available. There's an online section which is also full. There were 20 students in there. So right now we are already getting close to 60. I do not think we can accommodate more, unfortunately. Okay? If you are a CS graduate student and you need this class for your research, come talk to me. I'll see if there is a way I can accommodate you. Unfortunately, for the rest of you who have not been able to register, there isn't a whole lot I can do. There's a graduate course with 60 students is already very large, much larger than what we can accommodate. And I will just have to put you on a wait list. If somebody drops, I can accommodate you, but if not, I will not be able to accommodate you this time. Okay? I don't know why we have a big enrollment pressure. Usually we accommodate everyone who wants to take this class. At this time there was just a huge demand. I've already turned away almost 20 students, and there are still students wanting to take this class. Okay? That's just something that you should realize. It's not a whole lot of flexibility there. As you can imagine, a graduate course, as it gets larger and larger, there isn't a whole lot of discussion that can take place if you have a very large class. Okay, so just to keep it manageable, I have to cut the enrollment off at 60, and we are already at that level. Okay, so do write your name on the sign-up sheet. I will see if somebody doesn't want to take this class after hearing today's lecture and the syllabus, and if so, I can accommodate some of you. And if you are, as I said, if you are a PhD graduate student and need the class for your research, I can try to make some accommodation. So that's a slightly different case. All right? Okay. Any questions about enrollment before I actually jump into the syllabus? Anybody has any questions, comments? Okay. So I will start with the course outline. We'll look at the syllabus and so on. We try to make this course interactive. That obviously is only true for the classroom section. So if you're watching it on YouTube, you can't ask a question as you watch, but that's a separate problem. You can, so feel free to, for those of you who are here, please feel free to stop me, ask questions at any point. That's the best way to make use of the class time. Okay? So let's start with a quick outline of the course, what the course is about, what are the expectations, how we grade it, and so on. So I will start today with an introduction to distributed systems. We will look at what we mean by a distributed system, why they are useful for us to study, and what are the challenges in building a distributed system. Okay, so I should also mention, incidentally, the course official title for the course is Operating Systems. Okay. The working title has distributed and operating system, because really when you look at a graduate level course in operating system, a lot of the issues that come up really have to do with making the system more distributed. Okay, so we will actually, the topics will relate to both advanced operating systems and distributed system, a mix of the two. So it's really distributed and operating system. That's really what the course is about. Okay. So we'll start with that introduction. So you'll see in today's class, we'll talk a little bit about operating systems and a little about distributed systems. Okay. Next time, we are going to talk about distributed architectures. Okay. So broadly, how do you build distributed systems? What are the principles in building them and so on. Okay. And then we'll start actually going into the topics. Okay. So the first two lectures are mostly introduction, okay, just to build the right background. Okay. First topic, inter-process communication. This is going to be somewhat quick. We'll talk about remote procedure calls, remote method invocation, variety of techniques by which distributed systems communicate with one another. Okay, that's the first topic. Some of this material is typically covered in an undergraduate OS class as well. Okay, so I will review that for those of you who have not had a class in undergrad operating system. And the reason we go with this first is some of this is important as you do the first lab assignment. You will start building distributed system. You need to know how you are going to build your system or application. Okay, so that's the first one. Then we'll talk about processes scheduling. We'll talk about virtualization, code process migration, and so on in that topic. We'll talk a little bit about naming and location management. Okay, don't worry if these terms don't make any sense at the moment. As we go along, you will see that you'll see what they mean and how they relate to distributed system. Okay, so next topic, naming, location management. How do you assign names to entities in a distributed system? How do you resolve those names? How does location of an entity matter, and so on. There's a seed there. Okay. And then we go into sort of what I would call a core topic in the class, which is canonical problems in distributed systems. Okay, so we'll spend a good chunk of time on this topic. Okay, so here what we'll do is we'll take many of the problems that arise frequently in any distributed system design. We will abstract them out and we'll study them in the abstract. So we'll look at mutual exclusion, distributed mutual exclusion. You probably know what a lock and semaphore means. Okay, so we look at how some similar concepts are addressed in a distributed system. We look at leader election, clock synchronization, the notion of logical clocks. Okay, so these are problems that arise when you design a distributed application or a distributed system. Okay, so we are going to look at them in the abstract, look at algorithms on how to address them, okay, and in implementations of those algorithms. Okay. So once we have done that, then we are going to go into some other topics. The first one is going to be replication consistency. Okay. We'll see how you can use replication as a mechanism, a broad mechanism to build a distributed application. How do you replicate data? How do you replicate processes? What problems arise when you do replication? Okay, you need to ensure consistency of any data that is replicated. How do you ensure that consistency? What techniques arise when you do implement consistency? Okay. Then we'll look at fault tolerance. How do you ensure that when some entity in your distributed system fails, okay, you can keep the system going. Okay. In a centralized system, if there's any aspect of your system fails, your entire system comes to a halt. It cannot function anymore. In a distributed system, that does not have to be the case because the system is distributed. You can design it in a way such that failure of one or many entities concurrently still does not cause the system to stop. Okay, so important aspect. Okay, we're going to look at how do you do that. We'll briefly look at security. Okay, what are the security issues in distributed system? I won't dwell too much on this topic because now there is a graduate course in computer security. If you really want to know more about it, that's the class to take. But to the extent that you need to be aware of these techniques in a distributed system or a distributed application design, we are going to look at it. So it's going to be a quick overview of security issues in this. Okay? And then we'll have a set of case studies, as I call them, or advanced topics. We'll start with middleware, okay, distributed middleware. What kinds of middleware systems exist out there, how can we use them when you design your application, and a set of topics. Okay, that these topics keep changing. This is the set I think might make sense this time around. So we'll look at the World Wide Web. Okay. Interesting yet somewhat old topic. We'll look at cloud computing, interesting new topic. Green computing, interesting and even newer topic. So this green computing essentially means how do you make energy a design parameter, a design goal in your system. How do you design systems that not only meet many other goals such as performance, but also have a low energy footprint. Okay, becoming an important topic when you look at data centers and things like that. And we look at multimedia and mobile system. Okay, again, distributed aspects of multimedia and mobile system. Okay, that's a quick run through of all the topics in this course. Okay. So I will use course lectures most of the time. There will be supplementary reading in the form of papers and so on that I will put up. Some of those would be optional, so it's up to you whether you want to go deeper. Some of them would be required. I'll mention which one is which. Okay. And that's basically how we are going to go now. Okay. There is a book for the course, which is Distributed Systems by Tannenbaum. That's the recommended textbook. It's not required. If you don't want to buy it, you don't have to. You want to keep a copy or two in the library on reserve. You can go there, take a look at it. There'll be plenty of material that you can use from the course if you don't want to buy it. If you want to, feel free to go ahead and get one. It's a second edition. It's been out there for almost 5 years, so a used copy is going to get you just the same thing as a new copy. So if you can buy something inexpensively, feel free to buy it. Okay, which shouldn't be a problem. Okay. Even the first edition still works if you can still find it. The first edition is almost 10 years old, so everything you can get it easy. Okay, yes.
So I thought maybe you'll get to it, but the first assignment today was a reading from a book you referred to as AST.
Yes.
Is that this one?
Yes, Andrew S. Tannenbaum, that's the acronym of the author. So what we are going to do today is the first chapter. The question is, what was the reading? I did not really expect anybody to read anything because we haven't started the course, but I will put up course readings with the lecture. Okay? Typically lecture notes I will put up just before the class. The idea is if you want to print it and bring it here, you should be able to, and then take notes. But as you know, the class starts at 9 a.m. So if you want to print it, you'll have to come in earlier. I will try to put it the previous night, but I won't guarantee that that is going to happen. The class notes are ready. I'll put them in the lecture slides. Rather than ready, I'll put them in. Okay? So you'll see that everything, you don't really have to take notes on this. I'll post these things on the page, but it's always helpful to review things or bring it with you to class. Okay? So you can just take some additional notes. Okay. So that's the book. There will be a few others that I'll use from time to time, but you don't have to worry about it. I can make a photocopy of the appropriate material and hand it out. Okay. As far as grading is concerned, okay, there will be some homeworks, 15% of the grade. Programming assignment is basically going to be 40%. I'll be typically 3. Okay. 3 to 4 just to give us the flexibility. If we need to take a bigger one and partition it, but typically 3 assignments, okay, 40% of the grade. That is where you'll really learn. Okay, if there's one thing that you need to do to get the best out of this course is focus on the programming assignment. Because what the topics that we cover in the class, you will actually implement them in some shape or form in the assignment. Okay, so nothing like actually writing code to implement a technique. That's where you really learn how it works. Okay, some of those assignments, or maybe all, I haven't decided, will be group assignments. So you can actually form groups of 2 and work on those labs. And that's allowed, but then the expectation is that you actually produce something high quality if you're going to work in groups. Okay, 2 exams for the course, 1 midterm and a final. Okay, midterm typically is an in-class exam, closed book, closed notes. Typically the final is an open book take home. Okay, so 24 hours you get it, 24 hours you have to work on it and you submit it. Okay, so that's we'll probably use the same strategy here. In class midterm, closed book, take home, open book, final exam. Okay, that's also 40% of the way. Then class participation gets you something. Okay, so for the classroom section, that essentially means you have to ask questions. For the online students, of course, they cannot ask questions when they are viewing a video, but then we will have some simple quizzes on Moodle just to keep up with the class that relate to some lecture questions, and just doing those get you some points. Okay, that's true also for the classroom section. Okay, it's class mailing list. Typically, it's what we use to communicate, but I think it is open in the sense you can actually ask questions to the entire list. Use it with care if you don't send something and spam everyone, but we will use it just to ensure that you get important announcements about exams and whatnot. Okay, you don't have to sign up, you're automatically signed up. Spire will set the list up for us. Okay, so if you're registered, you're on the list. Okay. Prerequisites, this is, we don't actually enforce this strictly, but we just mention that. We are expecting that you have an undergraduate exposure to operating systems, that we assume you know something about operating system, because this is really a follow-on course to what typically an undergrad course looks like. Okay? If you don't have that background, I am not going to check. I will not ask you to drop. It's completely up to you. You can go take a book, undergrad textbook, learn the material, and you should be fine. There have been many occasions where students have not had that exposure because they don't have an undergrad CS background or whatever, and they have done fine in the course. Okay? But there is some expectation that you know some of the material. So if you need help, I can point you to books or materials that you can use to sort of ensure that you have the right background. Okay? So, and the other important prerequisite is that you should be comfortable doing some programming. So there is 40% of the grade is lab assignments. You will do some substantial amount of coding, okay, 3 assignments. So although it's a group assignment, still you need to be comfortable writing code. Okay? If you haven't done significant amount of systems programming, I don't mean systems programming as if you have to do kernel programming. That's not going to be part of this course, but you need to know either C or Java or Python or some such thing that you use to write client-server applications and do something interesting. Okay? So that's something you should be comfortable with. If you don't know whether you have the right background, please feel free, come talk to me. I can try to understand what you've done and whether you have the right background. Any questions on this so far? Before I start the quick introduction. Okay, so I will point you to one more resource here, which is the the course page. This was the URL I sent out yesterday via email. Okay. It has the same information that I just mentioned, but the only thing I would add to that is the course syllabus, the official syllabus, which is what I was just describing, is all there. Okay. So you should go take a look at it. If you we don't give printed copies anymore, just to save paper. And then there is the schedule, which is where we post basically everything that is happening in the course. Okay? Lab, the lecture slides, assignments, we are recording the course, so links to audio and video lectures, all of that is going to be posted there. Okay? There is also a Moodle site for the class. Okay? And we will use Moodle essentially for you to upload your assignments. Okay? Because that way you don't have to turn any hard copy things that get lost, and then you say you turn it in and we can't find it and things like that. You just turn it in, it's timestamped, there is no ambiguity about whether you turned it in on time or late, everything is tracked. So we will basically have you upload all your assignments to Moodle. Your grades for those assignments will also be made visible on Moodle. Okay? And solutions will be posted. Everything else is going to be on this page. I'm not going to go and post the same notes again on Moodle, so that's just extra work for us. Okay? So we just use Moodle as a way for you to submit assignments and get feedback on your grades for individual assignments. Yeah, I don't know if any or all of you have used Moodle. Is there anybody here who doesn't know what Moodle is? Everybody has at least used it once, right? Okay. All right. Any other questions about syllabus? Any concerns about the work? It is some amount of work, not tremendous amount. It's not an easy course where you can just do little work and get by. There is some work involved. Okay. All right, so let's start with a quick introduction of why distributed systems are interesting to learn. We'll look at a definition of a distributed system. Essentially, I'll do a quick overview and somewhat of a history lesson as well. Okay. So the reason they're interesting is practically any system that you any computing system that you interact with today is distributed in some shape or form, whether it's your online bank, okay, whether it's Google, whether it's Twitter, Facebook. You can take any application that peer-to-peer file systems or file sharing system like BitTorrent If you use grid or cluster computing, if you used practically any e-commerce website out there, they are distributed in some way or another. Okay? So essentially any interesting system that's networked also tends to be distributed these days. So it is interesting to learn how these systems are built. Okay, what are the challenges, what are the advantages, disadvantages, why are they distributed to begin with. Okay, so that's basically what you will get out of this course. You will basically get a basic understanding of how these large systems, or maybe they are small systems, but they are distributed in some shape or form. They are built, what are the design principles. Okay? So basically it's useful to understand how these real world systems work. Okay? And we are going to cover basic principles. Right? I'm not going to promise you that you will know how Google works exactly. Okay? So that's not the goal of the course. But you will understand how distributed systems are built, so you will at least understand if you read a paper on that has some aspect about all the systems, what that paper is talking about. So you get that background. Okay. So let's talk about the definition. Here is a very broad definition, very simple one. Okay? So essentially it says a distributed system consists of multiple connected CPUs, okay, that work together. Okay, another definition is it's a system of multiple connected processors that have an interconnect of some sort of communication medium or a network. Okay. So essentially in any distributed system we need more than one processor. Okay. Typically processors essentially mean also more than one machine. Okay. And since it says working together, that essentially means that there has to be a way for these machines to communicate or coordinate. So typically these machines are also connected by some communication medium, typically a network of some sort, whether it's a wired network, wireless network, doesn't matter. Okay? Very broad definition, right? Simple one. Okay? And there's another one that is a slightly different way of thinking about distributed system. It's a collection of independent computers that appears to its users as if they are one larger logical entity, one large logical coherent system. Okay? Slightly different definition. It says these machines are effectively cooperating, coordinating, so that the abstraction they provide to the end users is like as if they are a single coordinated system. Okay? Now this definition is so broad that it also includes parallel machines. Okay? By parallel machines we essentially mean any multiprocessor or multi-core system. Okay? Now if you buy even a phone or a laptop or a tablet, it has typically more than one processor or more than one core. Okay? Now, if you run an application on that machine, it's multi-threaded, it would actually fall within this definition, which is multiple connected CPUs or cores that work together. Okay? So this broad definition includes parallel systems. And parallel system, another way to think of parallel system, they are what are called tightly coupled systems. Okay? The processors are inside one machine, the interconnect is your system bus, not really a network of some sort. Okay? But for much of the course, we are not really going to focus on parallel systems. We are actually going to look at what we call loosely coupled systems, where the machines are essentially independent machines and the network is a real network. But occasionally we will come and look at parallel systems as well when we talk about multiprocessor operating systems. So this is why I've given a fairly broad definition that encompasses parallel systems as well. But typically the definition is tighter than that. But we will use this more broad loose definition. Okay. Advantages and disadvantages. So why design systems in this way? Why should you design an application that runs on more than one machine at the same time? Typically, I assume so far you've mostly built applications that either a single process, or even if it's multiple processes, they reside on the same machine. Okay? Some of you may have actually built a distributed application, but the processing is actually divided, partitioned across multiple machines. So what do you get by doing this? Okay. First advantage is that it allows you to share resources. Since you have multiple machines that are part of your distributed system, all the resources on each machine is also available to the component of the application running on another machine. Okay. So simplest example I can give you is a distributed file system, a client-server file system. Okay. You have data that resides on server, the disk is on the server. Okay? You can mount it as a network drive on your machine, and you can access files that are on a remote machine. Okay? You don't think of it in this way, but your distributed application in this case is your file server, your file system rather, and it has made resources, i.e. disk storage and disk files that are sitting on another machine accessible to you on this machine. Okay? Same is true of the World Wide Web. You basically are accessing HTML files or images or video or whatever it is. All the data that resides on another machine has been made available to you. Okay? That's just one example of resource sharing. Okay? It enables communication clearly. So you can do any application you use, whether it's Facebook or email or webmail, okay, that's all enabling communication at some level. Okay, for the users, they also enable communication at a lower level. Okay. So that's the first advantage. Second advantage is that basically you get economies of scale. There's a good price performance argument to be made as to why build systems in a distributed fashion. Okay, so let's take an example of a website that you put up. Okay, maybe it's your blog, maybe it's an e-commerce site where you have a store, online store that's selling something. Okay, when you build it the first time, maybe you don't expect a lot of users, so you put the entire system on a single machine. Okay, so you say that my website or my store is not going to get a lot of users, single machine suffices. And maybe for a period of time that's true. Okay, but then let's say that your e-commerce site or your blog or whatever it is starts becoming popular, lots of users start visiting it. Okay, so at some point in time, your single machine is going to get overloaded. It will not be able to service all of the requests that are coming to it concurrently, just because the load that these requests impose on the server is going to saturate some resource, whether it's the CPU, disk, memory, something gets saturated, the machine becomes a bottleneck, requests have to be turned away. So now you have to add more capacity to your site. The only way to service additional users is to add some capacity. So what are the two ways you can do this? Okay. First is you can put your site on a bigger server. Okay. You say I was running on 2 cores, I'm going to get a quad core system or an 8 core system, or I get more RAM, I get a faster disk, and so on. Okay. That's the first technique. Another technique is you basically say I'm going to go distributed. I'm going to actually put another machine and have both of these machines serve requests that are coming into my website. Is that clear what I said? So you can either make the machine bigger or you can add more machines. Okay? Now you can keep making it bigger, but there are going to be some limits. Okay? Maybe you made it bigger, you made 8 cores. What if your site becomes so popular that even 8 cores won't suffice? So you can only keep growing to some point, and at which point you may get the biggest machine money can buy, but then that's as big as you can make it. Okay? And as you can imagine, buying 8 core, 16 core machine makes this machine more expensive. Okay? It's much cheaper actually to buy dual core cheap machines, but have more of them and have them work together. So that's what I mean by price performance ratio. You can actually get the same capacity by adding lots of cheap machines that work together rather than buying a single more and more expensive machine. Okay. So you can essentially build distributed systems that give you good performance, okay, but at a lower cost if you design your application well. Okay. So that's another advantage of distributed system. It's sort of a cost or an economic argument. The third one is reliability and scalability. They're slightly different things. Okay? By reliability, we essentially mean that if some entity in your system fails, your application continues to run. Okay? So now let's take the example that I was just giving you. You have your e-commerce store. Capacity, to add capacity, you added a second machine. Okay? So now your store is replicated, is running on 2 machines. Now assume that one machine fails. There's a hardware crash on that machine. Okay. So if that happens, typically if you haven't designed your application well, your site is going to go down. It's basically not going to be able to accept requests. But if you designed a distributed system well, you should be able to take all the requests that are coming in and direct it to the second machine temporarily and have the site continue to run. Maybe requests get processed more slowly because the load has gone up. That machine is taking the load of two machines. So some request or some or all requests will be processed with higher latency, but the site continues to function. Okay? So you could design your systems to be more reliable if you design them well and it's distributed. Okay? This you could never do in a centralized system. If your site was running on only one machine, machine fails, site is down. There's nothing much you can do about it. Okay? That does not have to be the case in distributed systems. Okay? In fact, when we come to this topic, we look at it in more detail. If you have very large distributed systems, okay, that run on hundreds, thousands, tens of thousands of machines, failure is the common case. You have to expect that at any point, some fraction of the machines are either down because they have failed or have been taken down for maintenance. Okay? If you take Google, for instance, I mean, that the search engine essentially runs on tens of thousands of servers. Okay, distributed across tens of thousands of servers because the volume of requests is that high. Okay, when you have that many machines, it is to be assumed that some fraction of them will be always down because there will always be a fault. The probability of fault is going to approach 1 at that point, that some entity has failed. Or some node has to be taken down for maintenance. You want to do a software upgrade or something happens, so you need to clean things up and so on. So as your system becomes very large, designing for reliability becomes an important design goal. Okay? It's not an optional thing, it is something that you are required to do. And if you don't do that, you will see that there will be problems. Your entire system will go down. Okay? So that's one. And we'll come back to this topic, we'll look at it in more detail. Okay, scalability is the other advantage. Okay? Essentially by scalability, what we say is if you design your application well, as you add more nodes or more capacity to your system, the number of requests it can serve keeps going up linearly. Okay? If you have a 2-machine site, it should typically, if designed well, handle twice as many requests as a single machine can sustain. If you have 10 servers that are collectively serving requests, collectively you should be able to handle 10 times as many requests if you design it. So you should get, in the ideal case, a linear scale up. So now in practice you often don't get linear scale up, but in the ideal case, as you add more machines, the capacity should scale linear. Okay? That's an advantage. It's also a challenge. How do you ensure linear scale up? Because we will see that there are lots of issues that do not necessarily lead to linear scale up. Okay? The last but not least is potential for incremental growth. That was the example I just gave you about this website that starts up with one machine. Over time it gets more popular. You add a second machine, maybe then you can add a third. You don't have to buy the total capacity all on day one. You can slowly grow the capacity as the number of requests or the load that your system is trying to serve keeps going up. Okay? Any questions on the advantages before we look at disadvantages? Okay. So all this is what is great about distributed systems, but these systems don't come without challenges. Okay, so there are some disadvantages or drawbacks. Okay, the first is that it adds more complexity because your application or your system is partitioned or running on multiple machines. Okay, that's more complex than designing a simple centralized system. Okay, you have to basically deal with that complexity at the programming language level. If your programming language supports features that enable you to design distributed system, there are additional features you have to implement. It makes the OS more complicated. The OS has to have more components that enable this distribution, and it makes your applications more complicated. Okay, when you compare them to centralized systems, which are much simpler. Okay? So higher complexity, first disadvantage. Okay? Network connectivity is essential, the second disadvantage. If basically you need a network that is up and running. If any part of your network goes down, your distributed system is going to have trouble. You have network failure. You have to either design around that or deal with failure. Okay? So it assumes that a presence of a network that is up and running. Okay? Security and privacy is the third concern. Because now resources can be accessed remotely, that makes it more likely that there will be some security problem. And if you do not design your system well, somebody is going to find a hole enter your system and either get access to data, unauthorized access to data, or cause some problems. Okay? If you had a centralized system and the machine was not on a network, there is no trouble, and there's nobody, no remote attacks can take place. But when you design distributed systems, you have to deal with security and privacy. Okay, especially when you e-commerce sites that have credit cards and so on, you don't want these problems to occur. Okay, because you have heard of probably sites getting hacked into and credit cards getting stolen and all these bad things can happen. Okay, so you need to design for security and privacy. Okay, so next thing so that's advantages and disadvantages. And now I'm going to give you a broad brush overview of what we mean by transparency in a distributed system. Okay, so when you design this distributed system, as I said, things get more complex. Okay? So it is the job of the system designer to think carefully about what aspects of the system are you going to expose to the user and what aspects are you going to hide from the end user. Okay? And the claim is the more you hide, the easier it is for end users to use your application. And the more you expose and the more you want the user to do, the harder it gets for the user to use your system. Okay? And there are many dimensions of transparency, and I'm not going to go into all of these. I'm just going to start with an example to make you understand what transparency means. And then we look at a few of these and try to understand how, in that context, or an example, that kind of transparency was achieved. So let's start with Google, okay, the Google search engine. Okay, so if you want to type a search query, and you typically either go to the search box that's built into your browser window, but let's ignore that. You just say www.google.com. Okay, you'll go there, you'll get a search box. You just type your search query, and you hit enter, and you get some search results. Okay, so now think about this experience and think about how Google has designed its distributed system. So I already mentioned to you that Google, the search engine, runs on tens of thousands of machines. Okay? So when you go to the search box, has Google exposed to you that there is more than one machine that is going to process your query? No. Okay, that's hidden from you. When you type in a keyword and hit search, does Google actually ask you to specify which of those 10,000 machines should your search query go to? No, I mean, it figures it out, it sends it to the right one. Okay? So as you can see, lots of the details of how the system is built behind the scenes is hidden from the user. Okay? Think of an alternate approach to designing this search engine. Let's say you had the same kind of setup where you had the search engine distributed. And I tell the user, you figure out which of the 10,000 machines is closest to you, and you basically go and access that machine. So then I have to say, let's say, machine 1051.google.com, I actually do that, and then I go and connect to that machine and I send the query there. Okay? So now I impose the additional burden on the users, and you figure out, I have lots of these machines, you can connect to anyone, you pick one based on whatever criteria you choose, whether it's closest to you or fastest to you or whatever, you go connect to that machine and then you send the query to that server. Okay? That system is not transparent in many ways. It's not location transparent. You are telling the user, saying you need to be aware of which location and which server to connect to and send your query. Okay? So it's a very simple example, clearly, and somewhat contrived example, but what it is telling you is if you can actually hide lots of some of these unnecessary details from the user and make the system work, the users will actually get a better experience out of using your system. Okay, it will be simpler to use for the user, but of course there is more complexity in the back end. I mean, the system now has to figure out whenever a user comes in, which machine has to serve that user. Okay, how do I actually route the query to the right machine? All of that, now the system design has become more complicated, the user experience is better. Okay? There's always a trade-off. Right? You can basically dump more work on the user, simplify the system design, and maybe sometimes exposing more is good, sometimes exposing more makes the system cumbersome. Right? So there's no rule that says that everything, all these details have to be hidden. In some cases it's good to expose them, in some cases you shouldn't expose them. But And that's really depends on the application. But depending on what you do, whether you expose some feature of the system or not, you will say that along what dimension that system is transparent. Okay, so what I just told you about Google is what is called replication transparency. The fact that the search engine is replicated on tens of thousands of machines is hidden from the user. So the search engine is replication transparent. Okay? It's transparent to you that the system is replicated or not. If it wasn't, then you would say it's not replication transparent. Okay? So these are many different design parameters, right? So is it failure transparent or not? If some component fails, is that hidden from me or not? Will the system automatically take whatever I'm doing, move it to another machine? If so, it's failure transparent. If in the middle of doing something for me, if the one machine goes down and then I get an error saying I could not process your query, then it's not failure transparent. Okay? So you can have many things like this. So you can have location transparencies. I don't actually know where the machine is located, where the resource in this case, the resource, broadly the resource is located. Okay, I don't know where Google's data centers are. I don't need to know that. Okay, the system will figure out which location is best suited to serve my application. When you do Gmail, for example, or some sort of web mail, Google or Microsoft, doesn't matter. Okay? Typically, the system has figured out what is your location from where you are accessing, and your files are actually located in a data center that is somewhat close to you, at least on the right continent. So if you are from Asia, typically, and you have a Gmail account, your files may actually be stored on a non-US data center. And if you, when you created your account, you did it from the US, typically it may go into US data center. The system figures all that out. Okay, for you. Now at a later point, if you move, you don't have control over whether the data moves or not, because the system has hidden all that from you. Okay, so you may see that, hey, the mail access was pretty good when I was in my home country, but when I moved here, it's become slow. The reason it's become slow is your files are located pretty far away. Okay. Over time, the system will figure out that now all of your accesses are coming here, and it may transparently move all your files over to some nearby location. Okay. If it does that, you are essentially migration transparent, which means it figures out where the data should reside and where the accesses come from. Okay. And it does all these optimizations for you. Okay. So when you design a system, there are lots of these issues you need to figure out. Okay. What do you show the user? What do you do in the back without exposing any of these to the user? Okay. And you have to make good design decisions. Sometimes exposing certain features allow power users to do exactly what they want to do. Okay. Sometimes it makes the use of the system very cumbersome. Why is it asking me all these 20 things? I don't really care. I just want to access the function and be done. Okay. So important design principles that you will have to keep in mind. Any questions on this? So that's transparency in distributed system. Now we'll talk also about open distributed systems. Okay. Open distributed systems are essentially any system specifies clearly to you either its API, okay, these are the interface that it exposes to you, or the protocol that it is built on, so that you can write a component that interoperates with that system. That system is referred to as an open distributed systems. So you can write a system where you actually don't specify the interface, saying I am not going to expose the interface to any other developer. That's actually proprietary. Okay. That's referred to as a closed system. It doesn't expose. Many systems just expose their APIs. Okay. You can have, whether it's Twitter, Facebook, Google, they all actually have APIs that you can write things that interact with it in some shape or form. You can write your own client that can take some keywords and send them programmatically to the Google search engine, because there's an API that the search engine exposes to. This is how browsers actually have that box where you can type the query and they're able to communicate with Google, because the interface is exposed. You can use that interface to write additional application or newer application. Okay? So systems can be closed or open. Okay? Open systems are better because others can take your system and build on it. They can write new components that enhance the functionality of your system. Okay. Closed systems are not necessarily bad, they just happen to be proprietary, where you cannot actually extend the functionality of the system. The company or the designers or the group that designed it, they control how the system is evolved. Okay. There are many systems that are useful as well that may be closed. Okay. Whether to keep it closed or open depends on what application is it. Do you expect others to build on your system, or do you do not want to provide that functionality? So depending on that, you can make the system open or closed. Typically, if you make it open, it gets you benefits. Among them is interoperability. You can make the system portable. Others can write components or new versions of that system that exposes the same interface. It is extensible. And you can, as I said, you can extend the functionality of the system, evolve it over time, and so on and so forth. Okay. Many of the systems we will study will be open. Okay. There will be some case studies we'll look at systems that are closed as well. Okay. I just want you to be aware of what an open system means. Okay. Next thing we'll talk about is scalability in a little more detail. Okay. So this is essentially to understand what scalability in distributed system means and how distributed systems differ from centralized systems. Okay. So basically when we say a system is distributed, okay, there may be multiple dimensions along with it distributed. Okay. Whether the service is distributed, the data is centralized or distributed, or the algorithm is centralized or distributed. Okay. So depending on your system, it could be distributed in all of those dimensions or some of those dimensions. Okay. And let's look at examples to understand what each of those means. So let's take a centralized approach first. So if you had a centralized service, that essentially means there's a single server, okay, a single machine for all users. Okay. That's an example of a centralized service. Okay. On the other hand, if you have more than one server that collectively implements the service, your service is referred to as being distributed. Okay, that's basically the plain vanilla definition of what distributed system means. Okay. Now, assuming your system is distributed, so it could be the case that your data is distributed, your code is distributed, or both. Okay. In some case, your data may still be centralized. Okay. You may have multiple servers that are, let's say you have an online phone book. You know, if you can go to UMass People Finder, for example, that's an online phone book for UMass. You can implement it in many different ways. You can take all of the data for all users at UMass, you can put it into one big database, okay, and put that database on a single machine. Okay. In this case, your data is centralized. It's on one machine. But the front end, which basically is the web front end which accepts requests to search on this, that could be distributed. Okay, so just to make an example. So this is the data. This is your phone book data. That's sitting on a machine in the database server. That's centralized. Okay, so your centralized data, but you can actually have more than one machine that accepts search queries for your phone book. Okay, you're searching for somebody. And so now you are, in this case, I'm showing you two machines. Either of you can send your search query. Okay, let's say you're searching for me. So you will say, for Sheno, you can send it to machine 1 or machine 2. Either of these machines is then going to make a query to the database, get the reply, and send me back the response. In this case, the code is distributed, but the data is not. Okay, centralized data, distributed service.
But centralized service doesn't necessarily mean that the data is also centralized.
Yes, that's what I was trying to say. Right, so centralized service essentially means you can have more than one server, in which is this. You have 3 servers here. Okay? But you can have code being distributed, data being distributed, or either of those. Okay? So here's another example. A different scenario. Okay, same phone book, okay, but let's say there's only one machine. Okay, that's going to accept all the search queries, but I have taken the database and I've partitioned it onto 2 machines. Okay, let's say A to S, all last names that go from A to S is on this database, and then whatever S to Z or whatever is on this machine. the data is distributed. Okay, so when the query comes in, you look at the query saying, what's the last name? If it's in the first half of the alphabet, you send it to this database server. If it's on the second half of the alphabet, you send it to that database server. Okay. Same phone book application, different design. Okay, now I have only one machine, so code is centralized, all the code is running here, data is distributed. And I could have any combination of the two. I could have both. Right? I could have M1 and M2, I have both of those as well. Right? So I can have this scenario as well. Right? So when you design your application, you have to decide what's happening to the data. Is there one copy of the data in the system, or are there multiple copies? Okay? Or is the data partition? Okay? So that will tell you whether it's a centralized data, distributed / replicated data. Okay? And you say, ask the same question about the code. Is the code running on more than one machine, the same code, which means that more than one machine, either of those machines can service request, or is the code going to reside only on one machine? Okay, so you have this design flexibility. Okay. The ideal case for very good flexibility, both the data and the algorithms, okay, the code should be essentially distributed and or replicated. But you don't have to design all the systems that way. This depends on what you are trying to achieve. Okay? Right. So we'll talk, if you are designing algorithms or data that are decentralized, there are some principles you need to follow. Otherwise, even though you may have partitioned the data on multiple machines or replicated the data on multiple machines, your system will not scale. Okay? You will soon hit some bottlenecks. So the kinds of things you need to be aware of, there are 4 of them. Not all of them may make sense because we don't have the right background as yet. This is the very first lecture, but I'm going to mention this. And as we go along, we'll revisit these principles and understand how to actually put them into practice. Okay, the first thing is you do not assume that there is global state in the system, that no machine has complete state. Okay? You should, as far as possible, you should make design decisions based on locally available information. If a request comes in and I have to talk to 4 other machines to figure out how to service that request, that is going to impose some scalability bottleneck. Eventually, as the load grows, your system will have bottleneck. If on the other hand, when a request comes in, I have everything I need to know locally to service that request, I don't need to talk to lots of other machines to service it, that's a more scalable system and scale better. Okay? So you can make make decisions to service requests based on local information. Good principle before have in your system. A single failure should not bring down the system. Okay? If some machine fails, the system should not go down. Okay? You will see that in this example, single failure can bring down the system. If this machine goes down, site is down. You cannot accept your keyword. If this database server goes down, queries that start from A to S cannot be serviced. Okay? Partial failure. Okay? So you are going to have failures if you do not design your system. So in this case, single failure can bring down either the entire system or portions of the system. Okay, how do you design for that? And you should not assume something called a global clock, okay, which is if you assume that every machine is tightly synchronized and I'm going to use timestamps to figure out how to service requests and so on, soon that gets very messy because it's not possible to tightly synchronize the clocks on all of the machines. We haven't looked at any example where we still need clocks and timestamps as yet, but as we go along you will see that timestamps are actually used for a variety of purposes in distributed systems, and if you assume that clocks are tightly synchronized, you will see that there are problems again from scaling perspective. Okay? And if you don't understand some of this at the moment, don't bother, we will revisit this. Okay? Just something I wanted to put out in the first step. And the techniques you will use to achieve those principles, those are principles okay, that you want, the properties you want from your system. Okay, the techniques we will use are asynchronous communication, distribution and replication, and with replication comes consistency. Okay. These are the techniques we will use to achieve good designs. Okay. And we will look at communication, distribution, replication, they are independent chapters. Okay. And so the thing to keep in mind is the reason they are there is they allow us to build systems that scale well and achieve some of those properties. Okay, so that's basically a quick overview of some of the properties of this distributed systems and so on. What I'm going to do next is just do a quick history of evolution of distributed systems. So I'm going to stop for a few seconds, see if there are any questions. Anything at all? Okay, so let's look at the sort of evolution of how distributed systems have evolved, of distributed systems, how they've evolved over the ages. Okay. So the very early distributed systems essentially arose when there were these things called mini computers. Okay. What they were, basically, these were machines. These are not mainframe machines, but these are smaller machines that essentially had a network that allowed them to talk to another machine. Okay. The networks were typically telephone dial-up networks. There was really no internet at that time. You had a phone line and you could, and a modem connected to the machine. You could dial the number of another machine. It would answer, and now you have a communication line between those two machines, and you could basically send messages back and forth at a data rate of maybe tens of kilobits per second. Okay. Very low bit rate, but you could communicate. Okay. So this is how a very early distributed system looked like. Even with this somewhat primitive mode of communication, one application that really took off, which was email. So email was sort of one of the first very widely used distributed applications. But what you could do is you could basically have users. So let's say this is UMass and this is some other university. Pick one. Okay. So you could basically send an email. You could basically type the email and then you hit submit, and it would get queued up on this machine. Okay. Every hour or every half an hour, this machine would say, okay, where are these messages going? Maybe there are some messages that need to go here. It would then dial up that machine. Okay. Form a connection and say, here are 7 email messages that are being sent to your users, and then deliver them. That means from this queue, you would basically deliver some of those messages there, and then they would basically, that machine would then deliver it to the inbox of those users. So you essentially had this form of communication, and every once in a while you go and connect to some machine in the network, and then deliver messages that are sort of destined for that machine, and then you're done, and then you can do the same thing in the reverse direction. Okay? So it was not an always connected network. Every half an hour or every hour you would get connectivity, you would do something, and then you would disconnect. Nevertheless, basically it made at least things like email quite popular, because email doesn't have to be delivered instantaneously. It's okay if the mail is delivered 30 minutes from now. So long as it gets delivered in some reasonable time frame, it's still useful to send that message. It's still faster than sending postal mail for sure. Right? So that's how some of these early applications arose. In those days with mini computers, what essentially happened is all the processing was actually on this one mini computer, and then you use terminals, you could log into your machine, do some work, send messages, receive messages, and so on. Very early days. It also allowed you to do remote access for files. So if you had another machine on your campus, you could basically also run a distributed file server, which allowed you to take data that was stored on this disk and make it accessible on this. So you could do email, you could access data that was stored on remote machines and so on. Okay. So those were sort of the early days of distributed system, mini computer model. What came about next is what's called a workstation model, which is what is also used today, where processing became cheaper. So rather than having one centralized machine where all of the processing took place, you could essentially eliminate that machine and give each user a workstation or a PC that was powerful enough so all the processing could be done locally. And then these machines are all connected by a network. Okay, so workstation model simply means you have a machine that does local processing, has local disk, and is connected to a network. So all the processing can be done on your machine, and you can still communicate with other machines to implement whatever distributed application you want to implement. So this was sort of late 80s, early 90s. The cost of computing dropped to a point where it was feasible to buy every user a machine of their own, rather than having to go to a lab and go to a terminal and then do your computation jobs there, or run your computation jobs there. Okay. Those days machines still cost $5,000, $10,000. To buy your own machine meant you have to spend the order of 5 to 10 grand, quite a bit of money. But still it was not hundreds of thousands of dollars, so it's still cheaper, feasible to buy machine. Now with workstation models, workstation model of distributed computing, a whole new class of distributed operating systems, distributed applications arose. One that was quite popular was to do distributed batch processing. Okay? So what you would do is you would submit a job. Let's say this is your system, where there are all users, they're sitting in your office, each of them has their own machine, they're all networked, okay, using Ethernet or some such thing. You could submit a job to your machine, and maybe for a while it runs there. But then if it looks like your machine is overloaded, your job could actually hop to some other machine on the network. Maybe the user to which this machine belongs hasn't come in today. Okay? So that machine is idle. So your job could actually jump there in the middle and then start executing it. Okay? Because this machine is idle, it has somewhat more resources than your machine, which may be somewhat overloaded, your job can finish faster. Okay? This is referred to as job migration or process migration. So a whole set of systems were built that allowed you to make use of all the resources on your network, not just on your machine. Okay? Typically, even today, you don't. If you actually submit a command on your machine, you assume that it executes locally. Okay? That's the default model. But if you actually have job or process migration enabled in your system, it doesn't have to execute locally. Your system can decide which is the fastest machine available to it and actually execute that job there and give you the results. Okay, so you may actually get better performance than if you had to do all your processing locally. So we will look at how do you do job migration, process migration and so on. Okay. So that's sort of the evolution of your distributed system from mini computer to the workstation model. Okay, and then once you had the workstation model, that naturally evolved to client-server model, where the workstations were powerful but not necessarily powerful enough. So you had this bigger machine sitting somewhere on the network, which we started calling servers, and then these machines were called clients, and more computationally intensive tasks were offloaded to servers. Right? So you would basically submit a request here, but then it may execute it. This could be a print server, for instance, where you submit a print job here, but you send it to the server and then it prints to a printer from the server. Or it could be a file server, it could be a web server, it doesn't matter what kind of server is it. Its servers are more powerful than clients and can have more resources and hence run services that clients can access and make requests. Okay, so server will then process the request and the results back. Okay. And that model is still quite popular today. It's led to the evolution of the World Wide Web and lots of other applications. Okay. And so another model that sort of lies somewhere in between is what is referred to as the processor pool model. Okay. And so in the processor pool model, what happens is you assume that the server that is sitting here is not one machine, but is a pool of processors. It could be logically looks like one big server, but it can be lots of little servers, or it could be a server with lots of cores or lots of CPU. So your pool of CPUs available to you. You submit your job or request, and some processor in this pool will actually service that request and send you the results. Okay, so it's not, think of it as not one server, but maybe more than one server. So you can collectively use all the processors on those servers, or it could be one large server which are lots and lots of cores. It doesn't matter which of the two it is. There are the servers in the back end have lots of cores or processors. When you submit your request, the system figures out which processor to use and sends you back the result. Okay. So that's called the processor pool model. That's how it evolved. It's still popular today. Cloud computing essentially is mapped on nicely to the processor pool model. Okay, some also to the client server, but not under the processor pool model. Okay. So although this is a historical evolution of how these systems have come about. Some of these ideas still exist today. And we'll look at how do you design your system to map into one or another model. Any questions on this? All right. So here are some newer systems. We have cluster computing or data centers. We'll have lots of things to say about that. Essentially, it's one large system that has lots and lots of servers, so racks and racks of servers connected by high-speed network that implement useful applications, as Amazon, eBay, whether it's EC2. There are many different interesting uses of cluster computing and data centers. We'll talk about that. We won't do a lot on grid computing because we are going to look more at cloud computing as an example, and there are similarities between grid and cloud computing. Okay? So these are all newer models that somehow have some combination of either the workstation model, the client-server model, or processor pool model, or some combination of those. So there's grid computing, there is distributed data centers, which is Google, Amazon, and so on, and there's virtualization and cloud computing. And we'll spend some time talking about what is virtualization, how is it used in cloud computing. I won't talk too much about it now because we haven't sort of developed the right background. Okay. And distributed systems continue to evolve. It's not like it's a static field. There are new applications coming up all the time. There are distributed pervasive systems. Essentially, it says that computation has become so cheap that you can essentially put a microcontroller practically into anything. Yeah, and so things that you don't even think are computer are essentially now have some computational capability. They have a network. Okay? So today, if you actually buy a new car, it has 6 to 8 microcontrollers. It has an entire LAN sitting in it. Okay? It is a distributed system in some shape. But when you look at a car, you don't think of it as a distributed. You don't even think of it as a computational block. Think of I'm going to drive from point A to point B. But it has enough computation in there to be classified as a form of a distributed system, although an embedded form of a distributed system, an embedded microcontrollers. Okay. You can have home networks, whether you have a cable box that can record movies, whether it's TiVo and so on. That's a full-fledged computer. It has networking capabilities. It's talking to servers, downloading or streaming content. Okay. Another example of a distributed system. Okay, you never thought that your television or entertainment system was a distributed system, but now it is, because it has computation in it, it's network and so on. The same is true of what's happening with smartphones and tablets and so on. Okay? They are basically using client-server computation. They are networked. Some part of the application run on server, some run on the client. Okay? So it is again participating or is part of a distributed system. You have other things like sensor networks and healthcare monitoring and so on. Okay? Forms of distributed systems. Tiny sensors that have microcontrollers, that have networking capability, that can track some aspect, okay, whether it's the temperature in a room, whether it's tracking the heartbeat on a person, or I even have one I can show you. So this is a small device that tracks how many steps you take. It's a pedometer. It has a Bluetooth connection, so it is continuously syncing to a server, so you can see how much exercise you get every day. Right? So this small device is a network microcontroller. It's a distributed system. Right? So the systems continue to evolve, and we will look at what are the issues in designing pervasive distributed systems versus cloud systems, which are much more resource rich. These are resource poor systems. Okay. So we have maybe 5 minutes. I'm going to quickly go through this. Okay, so that's all about distributed systems. Next 3 or 4 slides we'll talk about operating systems in particular and see how operating systems have also become more distributed in the same fashion as other applications. Okay, so we'll start with a uniprocessor operating system. Okay. So here we essentially assume single core machine, a typical laptop that today even the simple laptop has more than one core, but take the scenario where your laptop or a desktop with only one core, okay? And you have an OS running on it. That's referred to as a uniprocessor, single core, single processor operating system. Okay? The OS essentially, what is the job of the operating system? Essentially is a resource manager. Okay? It manages all the hardware resources for you. It provides an easier to use abstraction to end user. Right? You, the user of this machine, don't have to worry about when you create a file, which part of the disk should that file be stored on. Should it be stored on block 10, block 22? You don't actually worry about it. You just create the file. If there is storage space available, the OS decides this is where this file is going to be stored. You create you start up a new application. Let's say you start up your web browser. You don't decide how much memory it needs. Should it get 100 megabytes, 200 megabytes? OS is going to figure that out for you. Okay? It manages all the resources, all the cumbersome tasks of figuring out when you start a new task, or a new process, new application, how much resources should it get, where should the data reside. All of that is hidden from you. Okay? So the OS is essentially providing an easier to use logical interface to you, and it is managing all the hardware resources on your behalf. Okay? That's really the job of the OS. It's sort of acting as the arbitrator for these resources. It's acting as the manager of all of these resources. Okay? Now, uniprocessor operating systems have also evolved over time. They started off with what were called monolithic kernels, okay, MS-DOS, early Unix, where all of the OS kernel code was stuck into one entity. Think of it as one privileged process that starts up at boot time. Okay? So everything was in one entity. That made the design of the OS hard, because if you added any new functionality, you have to know how that functionality interacts with everything else that is in the kernel. Okay? So your size code base keeps growing, and then adding new functionality gets harder and harder, because you need to know how each of these things interact with anything that is already in the kernel. So the other way to design it, which is not monolithic, is what is referred to as a microkernel architecture. Right? The reason I put it up is it sort of shows you early days of how distributed operating system came about. In a microkernel architecture, you don't put all of the functions into one kernel. You design a very compact kernel that has some very basic functionality. Essentially, all that the kernel is doing, microkernel is doing, is providing protection, ensuring protection, and providing inter-process communication. Okay. A lot of the things that you normally would put in the kernel actually run as user space processes like any other application. So here's an file server. Okay. The file system is running as an independent process. Okay. Here you have basically memory manager is running as an independent process. It's outside the kernel. Here is your CPU scheduler, okay, running as an independent process. Okay. And these processes have to obviously talk to one another. Okay. You cannot, because if they were in the kernel, they would be interacting with one another. All that the microkernel is doing is it now allows the memory manager to talk to the scheduler of the file server and so on. So this is a new way of designing your operating system kernel, where you have a very compact microkernel, and practically anything you build is actually built in user space. You could even have user space device drivers, for instance. The device driver could run as its own user space process. When you make a request, it goes to the kernel, comes to the device driver then sends it back to the hardware. Okay. This is a more modular way of designing your kernel. Okay. So all this is great. Now the big disadvantage of microkernel architecture was that there was a big performance hit as a result of this design. Okay. Anybody care to guess why there is a performance hit?
Because it's communication costs.
Okay, that's true. It is communication cost, but what aspect of it?
Switching between kernel and.
So now, if in the monolithic architecture, all of this code is part of the kernel. Okay, so this component wants to talk to that component to make a function call. Okay, you essentially invoke a function that a CPU scheduler has exposed or so on. So it's basically function call. In the microkernel architecture, same interaction requires an explicit message that you send that goes to the microkernel and is delivered. What was a simple function call essentially becomes a message between two processes, orders of magnitude slower. Because the message has to be constructed, sent to the kernel has to deliver it. It's going to take a lot longer. Okay? So interactions between components of the kernel essentially become messages between processes, and that gives a significant slowdown. Okay? So it's a very elegant architecture, highly modular, much more secure, because if there is You can no longer take a bug in the memory manager and hack into the machine and get access to the file system. They're independent processes. If everything was in one kernel, any hole in any one entity compromises the entire kernel. Here you only compromise that process but nothing else. Right? So from a security standpoint and so on, this is much better. From a performance standpoint, it's terrible. Right? So as a result, no commercial operating system still uses this architecture. Although many have tried. Windows NT, this is a sort of ancient version of Windows, started with this architecture. Mac OS X started with this architecture. Then they saw performance problem and they slowly started taking important pieces and pushing them back into the kernel, saying this is too important to be running slow, let's put it back. Right? So you are again moving back to a monolithic architecture for performance reasons. Okay? So that's basically how things have evolved. So we seem to have run out of time, so I'm going to stop here. Okay? So we will continue. There are 2 more slides remaining. We'll continue that next.